Okay, so polar coordinates. What are polar coordinates? So every point in the plane can be described using XY coordinates, and we've been doing a lot of that. These are called rectangular or Cartesian coordinates. Descartes was a 17th century mathematician, but every point in the plane can also be described with polar coordinates, which is the distance from the origin and the angle from the positive x-axis. This is an example of a polar grid. Every angle gets its own axis, and when we rotate the axis, we get a positive side and a negative side. So here's our polar axis, is the positive x-axis. Polar axis. And that's positive there, and it's negative there. And that corresponds to theta equals 0. If we rotate it 30 degrees, we get the 30-degree axis, right? And the positive side ends up here, and the negative side, negative side ends up there. So, and if we rotate it 150 degrees, that's the angle 150. This is the positive side, because positive side of the x-axis rotates to 150, and the negative side rotates over there. So this is the positive side of the 150, this is the negative side. But you can notice here that the 30-degree axis is related to the 210-degree axis. We take our positive x-axis and we rotate it 210 degrees. The positive x-axis is down here, while the negative x-axis rotates up here. So 30 and 210 are separated by 180 degrees. The 30-degree axis is positive in this direction and negative there. The 210-degree axis is positive this way, but negative up there. But the line is actually the same. So the origin is called the pole, and the positive x-axis is called the polar ray or the polar axis. So suppose we've got the point 3,3 and the point -2,1. What are our polar representations? So I need, for x equals 3, y equals 3, what I need are an r and a theta, where r is the distance from the origin and theta is the angle from the positive x-axis. So here's 3, here's 3. So 3, 3 is up here. And there's our angle that we need to find. And we can just draw this triangle that looks like this. And there's the angle that we need to find, right? That's this axis. And this distance from the origin, that's here, that's the r that we need to find. So r squared is easy to find because it's a right triangle, right? 9 plus 9 equals 18. So r equals square root of 18. Theta, how do you find theta? Well, we know the opposite and the adjacent. So we can always use the inverse tangent. Theta is pi over 4 or 45 degrees. Okay. So -2, 1, x is -2, y is 1. That's a point over here. And then we can draw in a triangle, x -2, what's r? And then again, the theta we want is the theta from the positive x-axis. So it's this whole thing. So x equals -2, y equals 1. So r squared will be 4 plus 1, because it's the usual Pythagoras theorem, -2 squared plus 1 squared, which is 5. So r equals square root of 5. And the opposite over the adjacent, tangent theta equals 1 over -2, right? Opposite over adjacent. So we look for the inverse tangent of -1/2. And that turns out to be -26.5. 5/6 degrees. Right, and that's the inverse tangent you get. But remember, the inverse tangent is always going to be in the first quadrant of the fourth quadrant, right? So minus 26 degrees is down here. And we want the angle that's up in the upper right. So we add 180 to that. So the theta that we want is actually 153.44. So this is an angle whose tangent is minus 1/2, but is actually in the second quadrant, which is where our point minus 2, 1 is. So you can find the polar representations just by finding r and theta, because you know the opposite and adjacent. What are the rectangular coordinates of the point with these polar coordinates? So r equals 3, theta equals 260. Where is that point? Well, we're looking at the polar grid, right? This circle is 1 unit away from the origin. This circle is 2 units. This circle is 3 units. So r equals 3 means we're somewhere on this circle. And we're at an angle of 260 degrees from the positive x-axis. We know that that's 270 degrees. This is 180. The way this is set up is that these lines are separated by 30 degrees. So if we want 260, we're down here somewhere. So theta equals 260. So we're actually at that point. So we want to know what the x and y coordinates are, and we can draw in a triangle. And we know how to find the x and y coordinates. If you know r and theta, x is r cosine theta, right? Adjacent over hypotenuse equals cosine. So 3 cosine of 260 degrees is minus 0.53. Y is r sine theta. And that's 3 times sine of 260 degrees, which is minus 2.45. So that gives me my x and y coordinates for that point. Okay, what about these other points? R equals 3, theta equals 620. Well, 620 is once around the circle, because that's 360 plus some more. So 360 degrees plus something else. And what is that something else? That something else is, unsurprisingly, 260 degrees. So r equals 3, theta equals 620 means start at r equals 3, go around once, and then go around another 260 degrees, so you end up back at the same point that we did before. So here x is minus 0.53, y equals minus 2.45. What about r equals minus 2, theta equals 5 pi over 3? Well, 5 pi over 3 is the same thing as, 5 pi over 3 is this angle, which is 330 degrees. Oops, actually that's 11 pi over 6. Sorry about that. Got a little too rambunctious there. 5 pi over 3 is actually this angle. So this is the theta equals 5 pi over 3 line. Minus 2, though, remember that when we rotate from the positive x-axis, positive is down here, the negative side of 5 pi over 3 is up here. So we want to go 2 units in the negative direction. That means we're looking at this point. So that's the same point you get when r equals 2 and theta is 1, 2, 3, 4 pi over 3. No, 2 pi over 3. So x equals 2 sine of 2 pi over 3. And we know that 2 pi over 3 has a sine of 1/2. Cosine of 2 pi over 3. Cosine of 2 pi over 3 is 1/2. So x equals 1. Y equals 2 sine 2 pi over 3. And that equals 2 times 1/2. So x equals 1. That's 2 times root 3 over 2. So y equals square root of 3. And that's that point. So a minus r means you go in the other direction. Now here, in finding this, for this problem, we use the equation x equals r cosine theta to figure these out, and I switch the r to a positive one. But we could keep the minus 2 and the 5 pi over 3, and that would give us the same point. And you can check that by grinding that through. So polar coordinates, each angle gets its own axis. It's got a positive side and a negative side. If you have negative r's, you have to go in the negative direction. So here's a point. Its polar coordinates r equals 4 and theta equals 60 degrees, which the below coordinates refer to the same point. So you can sketch that. 60 degrees is up here. R equals 4 is there, so we're at this point, more or less. R equals 4, theta equals minus 60 degrees. Well, minus 60 degrees is down here, and R equals 4, so this one's different. R equals minus 4, theta equals 240. Well, 60 plus 180 equals 240. So the theta equals 240 axis is in this direction. If we want to go minus 4 in the theta equals 240 direction, that means going up this way, which means we end at the same point. So this is the same thing. 7 pi over 3. Well, that's more than 180 degrees. It's more than 2 pi. So that's going around the circle once, plus an additional pi over 3. But pi over 3 is 60 degrees. So this is the same point because you go 2 pi plus another pi over 3, and you end up there. R equals 4, theta equals minus 5 pi over 3. What angle is this? Well, that means we're starting at the origin, we're going around minus 5 pi over 3, and that actually takes us over here. And that's the same point. So every point can have lots of different polar coordinates. Every point has just one way to do it in x and y coordinates, right? X equals this, y equals that. But in polar coordinates, there are lots of different ways to combine things. You can have lots of different r's and thetas. Generally, most of the time, we want r to be positive and theta between 0 and 360, but that doesn't always happen. Okay, so what are the equations relating rectangular coordinates to polar coordinates? We saw a couple of these. And it's all based on our basic right triangle. If this is r, this is x, and this is y, that's theta. X is r cosine theta, y is r sine theta. R squared, right, it's the hypotenuse, so it's x squared plus y squared. Tangent theta is opposite over adjacent. So we can switch between x and y coordinates and r and theta coordinates by using these equations. So how do you convert equations from rectangular coordinates to polar coordinates? Use x equals r cosine theta, y equals r sine theta. Substitute and simplify and use trig identities when you can. So can we convert these into polar coordinates? Well, for the first one, x is r cosine theta plus 3 plus 180 squared. R sine theta, 180 squared equals 9. So a note here, this is going to be, well, if we FOIL this one out, we get r cosine theta, quantity squared, plus 6r cosine theta, should have little parentheses around my thetas, plus 9 plus r sine of theta, 180 squared equals 9. So the 9's cancel out, so that's nice. But as a note, if I've got r cosine theta quantity squared, right? The squared distributes a little bit because it's multiplication, and you get cosine theta quantity squared. And we have a special notation for trig functions that are squared. We actually put the 2 on the trig function. So this becomes r squared cosine squared theta plus, I'm going to move this over next to that, r squared sine squared theta plus 6r cosine theta equals 0. Okay, so how can we solve that? Well, I can factor out the r squared out of those first two. And then this whole thing is just 1. So r equals minus 6 cosine theta, because you can cancel out the r's here, 1r, and then move the 6 cosine theta over to the right. And so that gives me a nice polar coordinate version of this. And this is a circle that's centered at minus 3, 0. Now this is a circle that's centered at 2, minus 4. So what does that one look like? Well, same kind of deal. We get r cosine theta minus 2 quantity squared plus r sine theta plus 4 quantity squared is 44. Foiling everything out, we get our r squared cosine squared theta minus 4 r cosine theta plus 4 plus r squared sine squared theta plus 8 r sine theta plus 16 all equals 44. So I can subtract off a 20 from both sides, which helps a little bit. Like in the previous example, the r squared cosine squared plus r squared sine squared is going to condense to just being equal to r squared. So we end up with r squared minus 4r cosine theta plus 8r sine theta equals 24. And at this point, there's really not much you can do, right? You can't condense that any further. So it's complicated, but you can do it. X plus y equals 5. That's a nice line, right? Slope is minus 1. Y-intercept is 5. Right? Y equals 5 minus x. So what's that in polar coordinates? Well, that's r cosine theta plus r sine theta equals 5, right? Just replace the x with an r cosine theta, the y with an r sine theta. And again, you don't get much of anything that you can solve for. You can't get the r by itself if you want, but the cosine theta plus sine theta doesn't condense into anything particularly useful. Great, so there's how you can convert xy equations into r theta equations. Just replace the x with an r cosine theta, the y with an r sine theta, and see what you get. Sometimes it'll simplify, sometimes it doesn't. How do you convert from polar coordinates into rectangular coordinates? Well, this is the relationships between x, y, and r and theta. So plug those in, simplify where you can, or use cosine theta equals x over r and sine theta equals y over r, and simplify using this. So r equals 5 secant theta. Secant theta is 1 over cosine theta. If we multiply both sides by cosine theta, we get r cosine theta equals 5, and we know cosine theta equals, we know r cosine theta equals x, so that becomes x equals 5. Okay. Checking my notes real quick. So that's r equals 5 secant theta. R equals 2 cosine theta plus pi over 6. What's an xy coordinate for this? Xy equation for that? Well, cosine of two angles added together is cosine A, cosine B, minus sine A, sine B. So that's one of our identities for cosine addition. So R equals 2 cosine of theta plus pi over 6. Pi over 6, same thing as 30 degrees. This becomes 2 cosine of theta times cosine of pi over 6 minus 2 sine of theta sine of pi over 6. And we know that cosine of pi over 6 is square root of 3 over 2. Sine of pi over 6 is 1/2. So we end up with square root of 3 cosine theta minus sine theta, and that equals r. So how can we figure out a way to think about this in terms of x's and y's? Well, there's a couple different ways to do this. I would just, at this point, multiply both sides by r squared. Not by r squared, just by r. And that gives me a 3r cosine theta and an r sine theta. And I like r cosine theta and r sine theta because r cosine theta is x, r sine theta is y, r squared is x squared plus y squared. So this is actually a circle, and you can figure out what it is by rewriting it as x squared minus square root of 3x plus y squared plus y equals 0. To complete the square, we need to add to both sides square root of 3 over 2 quantity squared, which is 3 over 4, plus 1/2 squared, which is 1/4. 3/4 plus 1/4 is 1, and so we end up with x minus square root of 3 over 2 squared plus y plus 1/2 squared equals 1. So in algebra, you should have seen completing the square. I'm not going to go through it in details because we don't really need it, but you can see that this turns out to be a circle. So generally, if you have r equals something times cosine or something times sine, it's going to be a circle. R squared sine 2 theta equals 6. I think I have just enough space to do this because this one's actually pretty short. R squared sine 2 theta equals 6. Well, we know that this becomes 2 cosine theta sine theta equals 6, because sine 2 theta, the double angle formula, gives you 2 cosine theta sine theta. So I can rewrite that in a sneaky way. Like that. So divide both sides by 2. 6 divided by 2 is 3. Then I've got an r squared times cosine theta times sine theta. So I'll rewrite that as 1r times cosine theta, and then another r times sine theta. And that gives me xy equals 3, because there are cosine theta and there are sine theta. R cosine theta is x, r sine theta is y. So in going from polar coordinates to rectangular coordinates, it's really sort of looking for ways that you can get r cosine theta and r sine theta as expressions. And then you can just replace those by x and y. So what we can do to graph some of these things on Geogebra. So we'll stop this share. We'll go to a new share. It's my Geogebra thing. Oh, hang on one second. Need to bring that up. There we go. So, here's my Geogebra. There it is. Okay, so hopefully I'm sharing Geogebra now. So Geogebra allows you to plot complex things, but polar things, but you have to be a little bit careful. So if I want that first thing, which is r equals 5 secant theta, I can type in r equals 5 secant and then a parentheses. And now to get the theta, to tell Geogebra that you want to graph polar coordinates, you have to hit Alt-T. And that gives you a theta, and that gives you the vertical line x equals 5, which is what we thought it would be, right? And so there's that. The other one was r equals 2 cosine theta plus pi over 6. So r equals 2 cosine, and again, Alt-T, and that gives you the graph plus I need my pi. Oops, I need that to be inside there, plus pi over 6. And there's that circle that we wanted that to be. One of the problems with this is that with Geogebra trying to graph these things, if we wanted the last one, which was turns out to be the parabolas, r squared equals sine of 2 times Alt-T. Oh, it was r squared sine 2 theta equals 6, so I want r squared equals 6 divided by sine of 2 Alt-T. Is my equation. And if you try and enter it, it says, well, I don't understand what you mean by r squared. So it doesn't like the r squared. So we need to work on that a little bit. And so if we want to get polar graphs on Geogebra, it always has to be r equals something. And so we want r equals square root of 6 divided by sine of 2. And now you put an Alt-T there, you get that equation. And now we have our nice parabola, xy equals 3. That's the blue, not parabola, hyperbola, that's the blue curve. So you can get these curves, you can graph these things in Geogebra. You have to be a little bit careful. To graph polar coordinates in Geogebra, it always has to be r equals something. And then when you want to put in the theta, you have to hit the Alt button, and then Alt-T will give you that graph. Okay, so go back to the lecture notes. So how do you plot polar equations? You plot polar equations by plotting points and then connecting the dots. So cardioids are things of this formula. It's r equals a number plus sine theta or a number plus cosine theta. So how do you plot these? Well, 2 plus sine theta, we'll plot that first. And part of this is just knowing what the basic sine and cosines are. Remember that our two basic triangles, which I think we introduced very back at the very beginning of the class, the 30, 60, 90 triangle and the 45, 45, 90 triangle. So 0, 30, 60, 90, 45. All the numbers that we're going to have in this table are going to be 1 over root 2, and root 3 over 2, and 1/2, and 0. I'm going to use 1 over root 2 equals about 0.7, and square root of 3 over 2 is about 0.9, just to make the calculation simpler. So sine of 0 is 0, and then we just go up a bit. 1/2, 1 over square root of 2, square root of 3 over 2, 1, and then we go back down. 1/2, oh, square root of 3 over 2, 1 over root 2, 1/2, and then back down to 0 when you get to 180. Okay, so what are your r's going to be? Well, 2 plus 0 is 2. 2 plus 1/2 is 2.5. 1 over square root of 2 is about 0.7, so this is about 2.7. Square root of 3 over 2 is about 0.9, so 2.93. And then you go back down, 2.9, 2.7, 2.5, 2. So what happens when we go from, so what we've done here is the top half of the unit circle. Now we're going to go down to the bottom half. Sine is y, so in the bottom half, all of my signs will be negative. So minus 1/2, we start at 0 and climb our way back up. Minus 1 over root 2, minus root 3 over 2, minus 1, minus root 3 over 2, minus 1 over root 2, minus 1/2, and 0. Right? So it's the same set of numbers, just with minus signs when you're on the bottom of the unit circle, or between 180 and 360 for sine. So r is 2 plus minus 1/2, that's 1.5. 2 plus, again, 1 over 2 is about 7, so this will be 1.3, 1.1, 1, 1.1, 1.3, 1.5, 2. So it looks like a huge table to fill out, but it's really not that bad. So how do we go about graphing this? Well, we've got angles and we've got distances. So for this one, we go to theta equals 0, that's the positive x-axis, and we go out 2 units. That means we have this point. At 30 degrees, this is the 30-degree axis, we've got a distance of 2.5. So we go out 2.5. Now we don't have a 45-degree axis on this particular picture, but there's 45 degrees. How far out do we go out for 45 degrees? 2.7. So don't know exactly where that is, but it's around here. And then at 60 degrees, we're at 2.9. And then at 90 degrees, we're actually at 3. And then going around the other way, we actually mirror it. Let's see, and then we're at 2.5. And then back down to 2. So 180, remember this is the positive 180 side, we go out 2 units. So it's minus 2 on the x-axis, but it's 2 units away from the origin. So that's the 180 and the 2. And now for the bottom half, we start at 2 and then we go 1.5, 1.3, 1.1 down to 1. So again, we don't have the 45-degree angles, but there should be one there and one there. And at the angle that's 210, we go out 1.5. So this is the 210 angle here, and we go out 1.5 units on that. And then this one's the 225 angle that I had to draw in, and we go out 1.3 units on that. So this is 1 unit here, this is 2 units, so 1.3 would be about here. And then we go to 1.1 and 1. And then we have this sort of same set of numbers. Oops, that's at 1. This should be at 1.1. This should be at 1.3, 1.5, and back up to 0. So my graph looks kind of like that. Terrible drawing, but that's okay. But that's how you can graph them, right? As you go around, you graph the points and you see what you get. Interestingly, this is symmetric about the y-axis, but not symmetric about the x-axis or about the origin. So second table, what's cosine? Cosine starts at 1, and then it starts decreasing. So root 3 over 2, 1 over root 2, 1/2 down to 0. That's the first quadrant. Now in the second quadrant, cosine is negative, but we're going to start climbing again. So minus 1/2, minus 1 over root 2, minus root 3 over 2, and then we get to cosine theta is minus 1. And now we decrease back down to 0. So minus root 3 over 2, minus 1 over root 2, minus 1/2, back down to 0, and then we climb back up to 1. So that's how the cycle of cosine goes, right? So in the first quadrant, that's these angles, and the fourth quadrant, which is these angles, cosine is positive. In the third quadrant, which is these angles, and the second quadrant, which is those angles, cosine is negative. So 1/2 plus cosine theta, this will be 3/2. Again, we're going to think of this as being 0.9, 1/2 plus, we'll call that 1.5. 1/2 plus 0.9 is 1.4. We'll call this about 0.7. 1/2 plus 0.7 is 1.2. 1/2 plus 1/2 is 1. And then 1/2 plus 0 is 1/2. 1/2 plus minus 1/2 is 0. 1/2 plus minus 1 over root 2. Remember, this is going to be minus 0.7, so this is going to be minus 0.2. And then 1/2 plus this is about minus 0.9, so that's going to be about minus 0.4. 1/2 plus minus 1 is minus 0.5. So we've got some negative R values here. We have to be a little bit careful on how we deal with them. And then the numbers go back again. We've already calculated what minus root 3 over 2 would give us, so minus 0.4, minus 0.2, 0, 1/2, 1, 1.2, 1.4, 1.5. So those are various R values. So in the first quadrant, oh, and here's how do you graph this on a XY plane instead. So you have to sort of draw on your own angles. 30 degrees is something like that. 45 degrees is something like that. And 60 degrees is something like that. Right, so R equals 1. If we're going out on the theta equals 0 degrees axis, that'd be 1 is there. I should have had bigger numbers. Oh, we actually start out at 1.5. No. So 1.5 when theta equals 0. At 30 degrees, right, we're at 1.4. At 45 degrees, we're at 1.2. At 60 degrees, we're at 1. So we go 1.4 out 30 degrees. Remember that this is the hypotenuse and not the x-axis, so we're going out not quite 1.4 there. And 1 unit is about that distance. So 1.2 at 45 degrees, which is about here. And then 1 at 60 degrees, and 1/2 at 90 degrees. So there's our graph of the angles in the first quadrant. 120, so this is 90 degrees. If we add 30 to that, 120 is about here. 135 is the 45-degree angle out here, and 150 is an angle out there, and the last one is 180. So at 120, we're actually at 0. So on the 120-degree axis, we plot the origin. At 135, we're minus 0.2. So keep in mind that 1 unit away from the origin is roughly this circle. If we're 135 and we want to go minus 0.2, that means we have to go in the opposite direction, 0.2. And in 150, we want to go in the opposite direction because it's a minus 0.4. And so the opposite direction of 150 is here, and minus 0.4 is out there. And then when we get to 180, we want to go minus 0.5. The positive 180 is this direction. We want to go half a unit in the opposite direction. So that gives me this. So if I connect the dots for points in the top half, I get a curve that looks like that. So what does it look like on the bottom half? Well, 210 to 240, we're going to be going negative, so they'll be opposite. Where are my angles? Here's 210, 225, 240, and then 270 is down here. For theta equals 210, we're minus 0.4, and then minus 0.2, and then back down to 0. So for 210, we're minus 0.4, so this is the positive side. The negative side is in this direction for 210 degrees, so we're about a 0.4. 225, this is the positive side. The negative side is up here, so we'll be about 0.1. And then when we get to 240, we're back down to 0. So we get this little thing. And then we start climbing back out. When we're at 270, we're at 1/2, 1, 1.2, 1.5. So 270, we're at 1/2. And then 270, we're at 1/2. And then 1, we're at 300. And 300 will be about down here. And then out a little bit further, and back up to that. So our curve has got a little loop inside. Right? And that's because of the negative R values. So we can graph that on XY paper. You just have to draw in your own angles. Okay, so these graphs had some symmetries. This is symmetric over the x-axis, but not symmetric over the y-axis. And so how can you tell? So there's these tests for symmetries, and I just took this from the book. You can be symmetric with respect to the polar axis, right? This is the x-axis. So if you replace theta with minus theta and you get the same equation, then it'll be symmetric. Symmetric with respect to theta equals pi/2, that means I want to have this point mean that I have this point on it, but how do I get to this point from here? Flip it over the x-axis, which means replacing theta by minus theta, and then flip it over the origin, which means replacing r by minus r. So if you replace r theta with minus r minus theta, oops, should just draw right through that with minus r minus theta, then you get symmetric with respect to the y-axis. And symmetric with respect to the origin just means if you flip r to minus r, you get the same point on the graph. So an important point, and this is why it's underlined, if the test works, you have the corresponding symmetry. If the test does not work, we don't know. It might not. So r equals 2 plus sine theta, test for symmetries. So we want test for the x-axis, y-axis, and origin. We replace theta with minus theta. So r equals 2 plus sine theta. That's our original equation. We replace the theta with a minus theta. We get r equals 2 plus sine of minus theta. We know theta is odd. So that means the minus sign can come out. And odd function, that's why we can do that. And so not the same, right? We don't know if this will be symmetric about the x-axis. Is it symmetric about the y-axis? Replace theta by minus theta, r by minus r. So that means we take r equals 2 plus sine theta, and we make it into minus r equals 2 plus sine of minus theta, or minus r equals 2 minus sine theta because it is odd. Or finally, r equals sine theta minus 2, which we do by multiplying both sides by r, and that's not the same equation, so that didn't work. What about the origin? R, that means replacing r by minus r, so r plus 2 sine equals 2 plus sine theta becomes minus r equals 2 plus sine theta. Multiply both sides by minus r, by minus 1, and we get that. And that test for symmetry doesn't work. But if we go back up to the graph of 2 plus sine theta, we see it is actually symmetric about the y-axis, or it would be if I could draw competently. So this has y-axis symmetry. But our test didn't pick that up. So the test can pick up symmetries, and if it does, then you've got that symmetry. If it doesn't, then you don't know. You just have to graph it and see what you get. What about r equals 1/2 plus cosine theta? Same deal. With the x-axis, we replace theta by minus theta. What does this become? That actually just becomes the same thing again, because theta is even. And so this one should be symmetric about the x-axis. And if you actually go up and look at the graph, right, it does have x-axis symmetry. The top half and the bottom half look the same. It doesn't have the other, it's not symmetric left and right, and it's not symmetric about the origin. So I'm not going to bother with the test for that. But this test does in fact pick up that it does have x-axis symmetry. So the tests are there, they can be useful, but not all the time. You have to remember that sine is odd, so minus signs can come out of sine. Cosine is even, so minus signs inside of cosine go away. So what are some other polar graphs? Well, there's a bunch of them. A Limassol has this kind of an equation. How do you graph that? Check for symmetries. It's a sine function, so if you actually check for symmetries, you're not going to get any. Sine functions, the tests for symmetry don't work very well for sine functions. But how do we figure out what is the plot of this Limassol look like? So sine theta, how does sine theta go? Oops, pen didn't work. Sine theta starts at 0, and then it climbs 1/2, 1 over root 2, root 3 over 2, 1, and then it goes back down, root 3 over 2, 1 over root 2, 1/2, and back down to 0. And then it goes negative, minus 1/2, minus 1 over root 2, minus root 3 over 2, minus 1, and then it goes back up to 0. So minus root 3 over 2, minus 1 over root 2, minus 1/2, 0, right? And you should be able to fill those kinds of tables in without actually doing much calculation at all, right? It's all 30, 60, 90 triangles and 45, 45, 90 triangles. And remember that we're going to call 1 over root 2 equal to 0.7, and we'll call root 3 over 2 equal to 0.9. So 3 times this is 2.1, 3 times this is 2.7. We'll need that a little bit. So sine theta is 0, 2 plus 0 is 2. Sine theta is 1/2, 2 plus 3/2 is 3.5. Sine theta is 1 over root 2, that's 0.7. So 2 plus 2.1 is 4.1. 0.9, 3 times 0.9 is 2.7 plus 2, 4.7. Sine theta is 1, this becomes 5. So then we go back down again, 4.7, 4.1, 3.5, 2. Okay, so when theta is 210, sine theta is minus 1/2. So this is 2 minus 3/2, so that's 0.5. Minus 1 over root 2 is about minus 0.7. 3 times minus 0.7 is minus 2.1. So this is minus 0.1. Note that we have negative r, so we're going to have to be careful about that. Minus root 3 over 2 times 3 is minus 2.7. So this is going to be that. Minus 3 plus 2 is minus 1. And then we go back up. So filling out these tables is not too bad because there's so much repetition. And once you get used to the pattern, it's not so bad. So when first quadrant is these numbers, then we go 2, 3.5, 4.1, 4.75. So 2, 3.1 at 45 degrees. We're at, what was that? 4.1 is out here, and then 4.7 and 5. So there's the points in the for angles in the first quadrant. Connect those. We get a graph that looks like that. What about in the second quadrant? That's these numbers, right? We start at 1 and then we just climb back down. And it's entirely symmetric. As we go through here, our 45-degree angle will be in here. That's a little bit more than 3, and then it comes back down to 2. Right, so sine theta is positive, same numbers, right? So generally sine things are generally symmetric over the y-axis. So what happens in the third quadrant? That's here, where we start out at 180 equals 2, at 210 we're at 0.5. 210 we're at 0.5, so this is my 210 axis. 0.5 is here. At theta equals 225, we're minus 0.1. So 225 again is this line. Positive 225 axis is down there. The negative is on that, and we're actually out a little bit here. 240, we're minus 0.7. So this is the positive 240 side. So the negative 240 side is out this way, and then 270, we're actually up at minus 1. So our graph at 180 is here, then we go through the third quadrant, and it actually loops up like that. And then if you plot the other points, you'll see that it actually loops back down and around like that. You can plot these other points. So that's the curve we get. It's called a Limassol, which is a French word. And it's got, because the r's are negative, you get a little loop in the side. Roses, r equals a sine n theta, r equals a cosine n theta, where n is a positive whole number. N is even, you have 2n leaves. If n is odd, you have n leaves. Again, this is a straight up sine function, so the symmetry things aren't actually going to work. The symmetry tests don't work for that. Oh, it does actually. The origin does. Check for symmetry. So x-axis symmetry is switch theta to minus theta, and r equals 2 sine theta. That equation would become r equals 2 sine minus theta, which is r equals minus 2 sine theta. So that gives me no information. Y-axis symmetry is replace r with minus r, theta with minus theta. And here, we get minus r equals 2 sine of minus theta. Sine is odd, so the minus sign comes out of the sine, and now the thetas cancel out. So we will be symmetric with respect to the y-axis, and we actually did pick that up here. Symmetric with respect to the origin, that's replacing r with minus r, but that just gives me r equals 2 sine theta becomes minus r equals 2 sine theta, or r equals minus 2 sine theta, which is not the same equation. So no information there about symmetry about the origin, but it'll definitely be symmetric about the y-axis. Okay, so how do we graph this? We don't want to have a zillion angles. But I'm going to start with the 4 thetas. I'm going to start with these angles. And why do I pick these angles? Because 4 times these angles are our familiar 30, 60, 90 triangle. 30, 60, 90, and 45. So 4 times 0 is 0. 4 times pi over 24, though, is pi over 6, right? And pi over 6 is 30 degrees. 4 times pi over 16 is pi over 4. 4 times pi over 12 is pi over 3. 4 times pi over 8 is pi over 2. And we know the signs of these things. The sine of 0 is 0. Sine of 30 degrees is 1/2. Sine of 45 degrees is 1/√2. My tablet is being a little bit weird. And that's square root of 3/2. Not sure what's going on there. Let's hope that fixed it a little bit. And sine of pi over 2 is 1. So 2 sine 4 theta, that will give me 0, 1, square root of 2, which is about 1.4, and square root of 3, and 2. Multiply those out. Okay, so that gives me the numbers. The problem is that on my graph, I don't actually have all these things. So we'll finish this off to get down to pi over 4. Pi over 6 times 4 is 2 pi over 3. And the sine of that is, man, bad time for my tablet to decide not to work. Let's try this again. Square root of 3/2. 3 pi over 16 times 4 is 3 pi over 4. And the sine of that is 1 square root of 2. And 5 pi over 24, if you multiply that by 4, becomes 5 pi over 6. And that has sine 1/2. And then pi over 4, if you multiply that by 4, that gives you 0. Okay, so, and then the numbers just work the way back down. So up to pi over 4, if we go from, the angle goes from 0 to pi over 4, our R value goes from 0 up to 2. So here's pi over 4. And halfway out to pi over 4 is pi over 8. And what happens as we increase the angle from theta equals 0 to theta equals pi over 8, our R value goes from 0 to 2 and then back down to 0. So it's 2 here, and it's going to climb from 0 up to 2 and then back down to 2. Okay, so what about from pi over 4 to pi? What are we going to get? Well, we've seen before that we'll get sort of the same angles, except all the signs will be negative, because we're going to end up with, if we go with theta going from 0 to pi over 4, 4 theta goes from 0 to pi. So pi over 4 to pi over 2 means that 4 theta will go from pi to 2 pi, which means that all the signs will be negative. We'll get the same numbers in the same order, except they'll all be negative. So what does that mean for our graph? From here to here, R is negative, which means we'll be in the opposite quadrant. We're not going to have R values graph up here, and in fact be down in the other direction. And it'll peak again at 2. So here's 2. So about here. So we get a graph like that. And then from pi to 3 pi over 4, our sine is going to be positive again. So we go out and back in. From here, from 3 pi over 4 to pi, our sines are going to be negative again. So that means we'll get not a graph in this part, but a graph over in this area. And I'll go out to 2 and back in. Okay, so from here to here will be positive again. So we'll get another leaf that comes out here. From here to here will be negative again. So then that gives us a leaf that comes out here. And then we'll have another leaf that's positive down here. And then in this last bit will be negative out here. And there's the graph of my rows. And everywhere through here, the maximums, we go out, that's pi over 8. This is 3 pi over 8, right? Because this is pi over 4 is 2 pi over 8. And then 5 pi over 8, 7 pi over 8. That's what all my maximums are. And so we get this nice rows. And it is symmetric about the y-axis. It's also symmetric about the x-axis, but we didn't pick that up. And it is symmetric about the origin, but we didn't pick that up with our symmetry tests either. And so here, my n is even, so we have 2 n leaves. If n is odd, we end up having just n leaves. So this would be a 3-leaved rows. 6 cosine 3 theta, check for symmetry. X-axis symmetry, replace theta by minus theta. So r equals 6 cosine 3 theta becomes r equals 6 cosine minus 3 theta. But cosine is even, so that becomes cosine of 3 theta, so you can actually just drop that out. So it does have this symmetry. It'll have x-axis symmetry because cosine is even. Does it have y-axis symmetry? And that means replace theta by minus theta, r by minus r. That's not going to work because the minus theta, as we saw above, disappears. We get r equals 6 cosine minus 6 cosine 3 theta. So we don't actually get any information there. And then finally, for the origin, if we replace minus r by r, we get minus r equals 6 cosine 3 theta, or r equals minus 6 cosine 3 theta. And now we know that, oh, and yeah, and there's nothing you can do there because the you got the minus sign there. So it doesn't give you any information about that. 6 cosine 3 theta. Oh, let's make it 4 cosine 3 theta so that I actually have enough space to graph this. 3 theta. So that means every 120 degrees, I want to calculate things. So we're going up to 120 degrees, which is pi over 3. That's 240. No, pi over 3 is, yeah, that is 120 degrees. No, that's not. I want this to be 2 pi over 3. That's 60 degrees. Never mind. Okay. So 3 theta, 0. Pi over 18 times 3 is pi over 6. Pi over 12 times 3 is pi over 4. 3 times pi over 9 is pi over 3. 3 times pi over 6 is pi over 2. 2 pi over 9 times 3 is 2 pi over 3. Pi over 4 times 3 is 3 pi over 4. 5 pi over 18 times 3 is 5 pi over 6. And then pi over 3 times 3 is pi. So pi over 3 is 180 divided by 3, so that's 60 degrees there. So what's the cosines, right? And so these angles I chose so that 3 times those angles are my standard angles. So cosine of 0 is 1, root 3 over 2. For some reason it's always in this table that I have issues with my thing. Pi over 4, cosine of pi over 4 is 1 over root 2. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. And then we go negative. Minus 1/2 minus 1 over root 2 minus root 3 over 2. And then, what's the last one? Minus 1. So the numbers in this column are the cosines of these numbers, but we're going to plot them for these angles. So what's R? And again, I'm going to make this 4 so I have enough space for this. 4, 2 square root of 3, which would take square root of 3 to be 0.9, and that'll be 1.8. This will be 4 over square root of 2, and square root of 2 is about 0.7. So this is actually 2 times square root of 2, so this is about 1.4. 1/2 times 4 is 2. I'm not quite right. That's 4. This should be 2.8, I think. 8 times 2. No, that's right, 1.8. 2 times square root of 2 is about 1.4. 1/2 times 4 is 2. That shouldn't be getting bigger there. Okay, got a little ahead of myself. This should be about 3.6. This should be about 2.8. That would be 2. This would be 0. Now this would be minus 2. This would be minus 2.8. This would be minus 3.6, and then minus 4. Okay, so we're going up to pi over 3, and halfway through we get to 0 at pi over 6. So we're starting out at 4. Right, and then we have to figure out at pi over 6, we're actually back down to 0, which is here. And in between pi over 6, we have these 3 angles, pi over 18, pi over 12, and pi over 9. And they split this into 3 bits. This is pi over 6, 30 degrees. And our graph is 3.6, 2.8, and 2. So 3.6 is about here, 2.8 is about here, and then 2 is there. So for these angles, our graph looks like that. And then for the next batch of angles from pi over 6 to pi over 3, right? Pi over 6 to pi over 3, all our r's are negative, so that means for thetas between these two, the graphs are actually going to be down in this quadrant on the other side. And it'll look exactly the same. It'll come out to 4 here. Right? What about the next batch from pi over 3 to pi over 2? Well, we get the same shape because it's always the same numbers, but my r's, that's the pi over 3 to pi over 2, and then that's the pi over 3 to pi over 6. So we get the same shape, and my r's will still be negative because I'm climbing back from -4 back up to -2, so it'll still be negative, and we'll come back this way. So from here to here, over the next 30 degrees, will be positive and climb back out to 4. Over the next 30 degrees, we'll still be positive and we'll drop back down to 0. Over the next 30 degrees, we'll be negative and we'll climb back out to 4. And we actually come back to where we started. And so over the next 30 degrees, we'll be negative and climb back down to 0. And then we just repeat the rows again. And so we end up with that rows. And it is symmetric about the x-axis, but it's not symmetric around the other two. And it's only got 3 leaves because if this is odd, you're going to cover the rows twice rather than just once. And so there's the rows. And finally, a lemniscate, we have to be a little bit careful about 2 theta. So this is r squared equals sine squared 2 theta. We have to be a little bit careful about this because, again, we chose the numbers here so that when we double them, we get our familiar collection of angles. Uh, 3 pi over 8 becomes 3 pi over 4, and then 5 pi over 6, and then pi. So sine squared of 2 theta, sine of 0 is 0. Squaring it gets you 0. Sine of pi over 6 is 1/2. When you square it, you get 1/4. Sine of pi over 4 is 1 over root 2. When you square that, you get 1/2. Sine of pi over 3 is square root of 3 over 2. When you square that, you get 3/2. And then sine of pi over 2 is 1. When you square that, you get 1. This becomes 3/4 actually. There we go. And then sine squared will decrease. 3/4, 1/2, 1/4, and 0. So r squared is 8 times this, so that's 0. 2 is r squared. 8 times 1/2 is 4. This becomes 6. This is 8. This is 6, 4, 2, 0. So what's r? Square root of 0 is 0. Square root of 2 is about 1.4. Square root of 4 is 2. Square root of 6 is about 2.4. Square root of 8 is about 2.8. And then we do square root of 6 again. Square root of 4 is 2. Square root of 2 and 0. But this is r. We're getting it by r squared. So in fact, all of these things should have plus minuses in them. You actually have 2 options for r. So great. So when theta is pi over 12, which is half of pi over 6. Oh, well, when theta is 0, it's 0. Pi over 12, which is half of pi over 6, you have 2 possibilities for r. One is plus 1.4 and one is minus 1.4. So we actually get 2 points, one here and one out here on the negative pi over 12. Likewise, for pi over 8, which is 1/2 of pi over 4, you get 2 points, plus minus 2. So pi over 8 will be about there, and we get a point here and a point there. No, not actually on that line, but on the negative pi over 8 axis, which is about there. Right, and then we get a 2.4 at pi over 3, at pi over 6, and a 2.8 at pi over 4. So 2.6 here, but also a negative 1, which is down here. And then a pi over 4, which is about here, you get a 2.8. And opposite, you get another 2.8. And then at pi over 4 itself, no, at pi over 3, at pi over 6, you get 2.4. Yep. And then at pi over 4, you get 2.8. Yeah, there we go. So our graph looks like this going out, but also this, because you also have those negative r's. And then if you plot the other points, you end up with the graph coming back down like that, and we end up with that. Great, so that gives me theta's going from 0 to pi over 2. What about theta's going from 0 to, did not, I just cut and pasted and did not change these things. So I want these to all be in the third quadrant, so I want these to all be pi over 2 plus these things. Not the third quadrant. I want my angles to be in the second quadrant, because if my angles are in the second quadrant, then twice the angle is going to be pi plus pi over 6. I don't need the 0 there. This will be pi plus pi over 4. This will be pi plus pi over 3. Pi plus pi over 2, 270 degrees. Pi plus 2 pi over 3. Pi plus 3 pi over 4. Pi plus 5 pi over 6. And then pi plus pi, which equals 2 pi. So what do I know about the signs of these things? All these signs are going to be negative, but when I square them, I'll just get these same numbers again. And so I'll just get the same numbers again for that. And so we'll end up with something that should look something like the same thing, but going in that direction. So we end up with a graph that looks something like that. So plotting these things, if you have an r squared equals something, you have to keep in mind that we have a plus or minus. So as you graph it, you're going to end up with two sides of it. So that is that.